Oh, no, no worries.
Because I'm sure Catherine will get mad at me if I don't post.
Yeah,
So
gotta
Catherine,
get
that was
back.
for you. All right. So yeah. So let me
Yeah.
back up and re-explain what the thing is. So we're looking at Damon's asking about the two-tail test versus the one-tail test. So let's say you take a look at the national average. This is the national stat for the number of hours that students work outside of school, outside of their education. And so you suspect that that national hours for working is different in Humboldt County. You don't know whether it's less, you
Yeah.
don't know whether it's more, and so you say, okay, not equals. Then you go out and you collect your data and you get a sample mean among CR students that X bar is equal to 24 hours, the sample standard deviation of 5 hours. Now, it's not fair based upon this to come back in and go, oh, no, excuse me, I made a mistake. I didn't want this for my alternate, this being a not equals. What I wanted instead is I want my alternate to be that mu is greater than 17 hours. So that's what they're
So,
talking about in the book. You don't get to do that now that you've peeked and look at your data, change your alternate hypotheses, okay?
okay. So, my question is then because I did the discussion question and I've been starting to see the responses roll in. If we're talking about if we're talking about this one researching woman, and she's talking about she believes 6.1 inches is an understatement. Are
Right.
we is my original assumption was that it would be not equal to 6.91 inches because she thinks it's more than that, but I kind of don't understand where the greater part comes in. Is that just
Okay.
saying we think it's more than that? Because
Well,
I've been
this is the case where the researcher, has an opinion in which direction she's not taking the not equals case. In other words, she has an opinion of which way she thinks the actual
oh,
population mean is.
so it's if she didn't have an opinion, it would be the other way.
She just thought it differed, then she's going to use not equals. She just thinks it's not the same as what the status quo is, right?
Oh,
In
okay.
this case, not. She says, my research hypothesis is I believe that people have gotten taller and the 69.1 is too short. And so I'm going to
Okay, that I was
propose.
okay. I was a little worried.
Let me give you an example. It's another one we're going to be doing in the not too distant future is average body temperature.
Ooh, that's fun.
Well, if you think about it, I mean, every thermometer in the United States is set to say that the average body temperature, if you're healthy, mu is equal to 98.6 degrees Fahrenheit.
Yeah.
So that's the status quo. Okay, that's the norm.
Mm-hmm.
Well, there has been a lot of research or researchers that say, they don't believe that actually the average body temperature is less than 98.6 degrees Fahrenheit. And it's a classic example that's used in many stats books because it's pretty good. You can go out and, if we took a random sample of about 40 CR students and took their body temperature using a pretty accurate thermometer, we would probably get an X bar that would be less than 98.6.
Okay.
In fact, a lot of people have said that really the healthy body temperature is 98.2. Now that might not seem like a lot, but it's
Yeah.
probably why they
Well,
haven't bothered changing the thermometers. But it could be that's what you get, say, with a sample standard deviation of like say 0.92 degrees or something like that.
yeah. People would freak out more if it was Celsius.
Yeah, you can't even go there. Say with an n equal to 40, and if you go in now and you draw this normal distribution here, where we're going to go with the mean being 98.6. And we'll just agree not to disagree about that the standard deviation is 0.92. We'll use the sample one to estimate our population one.
Can I interrupt real quick?
Oh, please. No, go ahead.
Is the 0.92 is that the like 9? Oh, okay. I thought so though.
It's 0.92. It's the sample standard deviation. So this is This is the SD, and then
Yeah,
this is the
yeah,
mean. But
I remember that.
right, yeah, the first one here, this is the sample mean, and these are both sample values. In other words, they come from data that you sampled.
Okay, but where did you? Okay, now I see that, but where'd you get the 0.92 for the standard deviation? Now that's what
Over
I'm
here,
not getting. Yeah, and that's
so
a little lost.
the normal distribution is modeled by mu and by sigma, right?
Yeah, but we
Okay,
don't have sigma, right?
no, we have mu though because the null hypothesis gave us mu.
Yeah.
So what we do is we agree to not disagree and say, well, then that's going to be approximately the same as mu by s.
Okay.
And we're going to fix that in the next chapter. We're going to use a distribution called the t distribution that uses s instead of sigma.
All right. That makes more sense.
But for the moment, we'll just agree to go ahead and let s be sigma, and we'll roll with that. So the null hypothesis, what it says is it says that it's centered at 98.6 degrees Fahrenheit. Okay.
Yeah, it's like what everybody believes, right? Or
Exactly. So that's what the null says. It says this is the truth. So then you went out and you sampled 40 people and you got this value of 98.2. So what you can do with that,
computed like is, or no, you have to do a significance value. That's right.
right, but what we can do is we can actually
Yeah.
calculate z. And the way we can calculate z is we can take our 98.2 and we can subtract from that the 98.6.
Oh, just like the formula that you have to memorize.
Yes, exactly. The only formula I will make you memorize, divided by s over the square root of n. So that's going to be 0.9.
And it's gonna be negative. Yeah, it's gonna be like. I'm not very good at like numbers in my head with that.
I'm not doing that in my head. That's why I got R. I'll go get my console open here. Here, let's get the console up and
Yeah, I always control L the console.
yeah, exactly. So let's see, what do we need to do here? 98.2 minus 98.6. So 98.2 minus 98.6. Okay. And then divide that by 0.92 divided by SQRT of 40. Okay. And so that number right there, that's our test statistic. It's how many standard deviations
It's almost
value.
3.
Yeah, almost 3. How many? It's yeah, negative 2.8 if we round off, right? Well,
I was gonna say
2.75. Yeah, we'll go negative 2.75.
That's what I was gonna say.
So if you remember the little trick there, that's one standard deviation. So that would be about 2 standard deviations, right about there.
It's almost well.
And
Yeah,
it's down right about here-ish, right?
yeah. It's almost like not even really. I shouldn't say not important, but it's almost not significant enough to.
Yeah, it's really small. Okay, so that's at 98.2, falls right there in the distribution. And so what that means, based upon our researchers' hypothesis, this red shaded area right here, that's going to be our p-value.
Oh, okay, that makes sense.
Okay, so now notice something. If our researcher had done a not equals, then they would have had to also gone over and done the mirror image over here. They would have had to double that p-value and do that part up there also.
Oh, so they'd have to do the plus part of it?
Yes, they would have. But since up front, since they set their research hypotheses up front, you know, in such a way so that that's not going to be the case, right? Then you only have to do it in one tail. So notice your p-value actually going to be smaller. Your p-value is always half of what it would have been in a double or a two-sided test. A one-sided test is half of it.
And just I've seen in the book that they say normally a significance level is 0.05 or 5%. Is that what we're just going to use for this class, or will there be times that it's more like something else?
Depends. It can change. Typically, what you'll see in most scholarly work is that they'll use a level of alpha, or significance level, ranging from 1%, 5%, or 10%. And the way they decide which of those to use is based upon the severity of the type 1 error. If making a type 1 error is a really bad thing and you don't want to make a type 1 error, then they'll go with a smaller level of significance. If on the other hand, if maybe you're working with a bag of M&Ms and you're trying to decide, if the distribution of the red color is what Mars M&M says it is, well, then maybe we'll go 10% because it's not really that big of a deal if we falsely reject the null hypotheses. But if it's, the amount of acetaminophen in Tylenol is what is stated, and you are going to say that it's not, you may be causing undue hardship to, the company that manufactures it, and you may get yourself in a lawsuit. So you may want to have a much higher, higher standard for rejecting the null hypothesis than you would in the other case. So, but that said, Damien, the gold standard is 5%. No one would ever argue with you about using 5%.
Okay, because I just seen in the book that they had like other ones, and I'm like, okay, which one are we using?
I got a video next week says why 5%.
Oh,
so that you can watch that. This, where did this 5% thing come from?
I just thought it was a bunch of mathematicians said, that's the rule. Okay.
Actually, it was one.
Oh.
It was a one. It was a guy named Ronald Fisher, and most of what we're learning is credited to him. He was the great genius of stats back in the day. He was an Englishman.
Oh, yeah.
And he, off the cuff, said, because they asked, well, what level of significance should we use, And he said, well, 5% will suffice. You can use that. And it just stuck. And so now everybody uses 5%.
Okay, and then I'm just trying to, anything that's really, I was going to wonder, for when we do the midterm for confidence level, is it just going to be similar to when we did the summative quiz? Like you'll have a
yes.
I'm trying to word it properly. You'll have we want to know a 99 or 95% confidence level. Compute it, and you just compute it, and then
yes.
Okay.
Yes. Use Q norm to get your Z star.
Okay.
And then you're, that's how you're going to calculate your Z star, because here, I'll tell you what, I'm going to do confidence intervals in a minute. Let's finish this one off and go calculate this p-value, and then we'll come back and switch over to confidence intervals. Okay?
My bad.
No. We might as well. I mean, we're almost there, right? So let's go ahead and do it. So to do the p-value here, if we want to actually calculate that, that's going to be p norm, because we're working with a normal distribution, right?
And that's p-value is probability value, right?
Yeah, exactly. It's a probability value. It's a probability in making a type 1 error based on your observed value is one way of thinking about it.
Okay.
So
that's good to know.
P norm, since we're summing from the left, we're good to go. We're just going to put 98.2. We know the mean is 98.6 and the standard deviation is 0.92. And so if we put that command into R, P norm tab, let's see what we got, 98.2.
Yeah. I'm always really careful when I do these commands, because sometimes I've frustrated myself on homeworks by not paying attention.
Yeah, you gotta be careful what you type in. Okay.
So 33.
Oh wait, my bad. My bad. It's not. I used the wrong distribution.
Oh. Okay, why are you typing square root? I'm confused.
Let me do that first, and I'm gonna go back over and fix my drawing, because I messed up my drawing. This is the distribution of who?
The sample mean?
Yeah. So the standard error is what I need to put in there, not the sample standard deviation, right? So this needs to be divided by
the sample size, right?
The square root of the sample size. I mean, I did it right when I did the test statistic. I just forgot to do it over here.
Yeah, so it'd be,
So you got to remember, this is the sampling distribution of X bar, and to calculate the sample standard deviation of the sampling distribution of X bar, which is, by the way, we call it the standard error because it's just a mouthful to say the other way.
Yeah.
You take the sample standard deviation and you divide that by the square root of n, and that's going to give that for you.
Yeah.
Okay. So anyway, back at the ranch here, that's the correct probability right there.
Oh, okay. So that's a really small probability.
It is. And so we see that value, the p-value, which was, 0. Let's see, was it 0.03 if we round off, right?
Yeah, I always round off.
Yeah, definitely. Okay. Well, you see that that's less than 0.05. So your
So you
decision,
reject it.
you got it. You would reject it. Good job.
'Cause- And then if it's greater, you accept it. All right. Or no. Yeah, you accept it, right?
Well, you fail to reject it.
Oh.
In the next module, we talk some more about that, about how
Gotcha.
hypothesis testing in our legal system, a court case in our legal system, are kind of mirror images of each other. It's based on the same ideology, and so once you look at it from that lens, it makes sense why they say fail to reject.
Okay.
It's like if you think about the OJ, so for some reason OJ Simpson's popular again. There's a Netflix thing on it. There's all these TV shows about it.
I know.
But so a lot of people, in our judicial system. Let me go ahead and get a clean screen here. In our judicial system, the null hypothesis is that you're innocent, and then the alternate hypothesis is that you're guilty, right?
Yeah, guilty.
Yeah. Okay. So it is incumbent upon the prosecutor, who is the researcher, the alternate hypothesis, to produce evidence to persuade the jury that innocence is not a valid conclusion. In other words, we're going to produce evidence that shows that the hypothesis of innocence is so far-fetched that the only thing that we can replace it with, or the only thing we can assume, is that our person was guilty. So in the case of OJ, most people believe that he was actually guilty, but they failed to convict, right?
Yeah, I was a kid when that happened, so.
Yeah, well, they failed to convict, okay? So that's failed to reject.
Okay, that makes.
You get it? They didn't
Yeah.
convict him, so they failed to convict him. They didn't say he was innocent, did they? They said we failed to convict him, and since you failed to convict, that's the same thing as saying fail to reject.
Okay.
Double negation is a bit harsh, but that's kind of where it comes from.
Yeah, I've almost watched those documentaries, but then I'm like, I don't know if I want to get caught up in all that mumbo jumbo.
Yeah. Well, let's go talk about confidence intervals. Let's say now that you're kind of convinced that your sample has produced a more appropriate estimate of the population's true mean body temperature for humans, and so you want to set up a confidence interval for that.
Yeah.
A point estimate's great, but it doesn't tell you all that much about the error involved in it, and the error involved in it would be your standard deviation tells you something about that. So any confidence interval that you generate is going to be a point estimate, so just a single value.
Yeah.
And that is going to be plus or minus your margin of error.
And that's not the standard error, right?
The standard error is part of it, actually.
Okay.
The margin of error is based on the standard error.
Okie dokie.
All right. So in the case of when you're working with a mean, the point estimate is X bar. That's your sample mean.
Oh, okay. I remember. I think you put it in the wiki page a while back. I think.
That X bar is your sample mean. That's your estimate of the population mean, and then plus or minus. And then what you're going to do is you're going to move out Z star standard deviations.
So that's not Z to the something power?
No, it's just it's pronounced the way you say it is Z star.
Okay, because I need to go edit that because I think I put Z to the power of something.
No, it's just to let you know that it's a particular fixed value. And
Okay.
so what you're doing is you're using your sample mean as the center of your distribution, and you're moving out till you have what you consider, based upon your sample mean, let's say 95% of all possible values. So that's roughly going to be 2 standard deviations, right? It's not exactly, it's actually 1.96 or 98 if I remember correctly.
Yeah, I think the book uses 9.6. I think.
9.6, yeah, I think it's 9.6. Okay, so let's go back for just a second. Let's use the numbers we did in the previous problem. So you got X bar is equal to 98.2. got S is equal to 0.9, did I say 92, I think, if I recall correctly. And
Yeah.
then N was equal to 40. Okay, so if we want to make a 95% confidence interval, we've got everything we need to put it together. Look, I know what X bar is, I know what S is, I know what N is, I just don't know my Z star yet. And so Z star, what it does is it tells you how far to move to the left and the right of X bar. This point is X bar
Oh, okay.
plus Z star times S over the square root of N.
And the other one is the opposite, the left side.
Exactly. Exactly.
Okie dokie.
All right. So to do that calculation by hand,
Ugh.
the only thing I need to do is go figure out what Z star is. So.
Is that when you use a table?
Nope. I never use tables.
Okay.
R does it all for you. Do it all in R. It's really easy to do in R. You're much better off than learning how to use those stinking tables.
Trust me, I love R too.
Yeah, no, I mean, really, the hassle learning to use a table is actually more than it is to spend the time learning to use R. And it's not as accurate. So there's that part too. So when you've got an area and you want a position, you use Q norm. So that Z star is calculated from the standard normal. It's always from the standard normal distribution. It's the value of Z. And there's two of them. There's a negative Z star down here and a positive Z star up there, okay? And what I know is that this area is going to be the same. It's still 95%. I just need to know, since I'm working in either the table and or R, doesn't matter which I work in actually, I need to know that I'm working from a left tail, okay? So the command I'm going to use in R is going to require me to use a left tail. So if it's 95% in the middle, then what that means is I got 5% left over to give to my two tails.
Oh, okay. It's just sometimes when I read the book, it makes the mumbo jumbo sound, or I shouldn't say mumbo jumbo. It makes the jargon really confusing to understand.
Right, yeah, they don't say it in English.
Yeah.
They say it in math, which sometimes is hard. So what I'm going to do is to figure out, I want to know what those values of Z star are, okay? So to figure that out, I'm going to use Q norm. So Q norm, all I got to do is put one of these areas in the left-hand tail of that area, put in 0.25, comma 0, comma 1.
No, Mom, it's not. Sorry.
Oh, no worries.
I'm talking to my teacher right now.
It's okay, Mom, really. So if we go Q norm, and I put in 0.025, that's, 2.5%, comma 0, comma 1. There's the negative 1.96 that they're using in the book.
Okay, but where did you get the 0? I was following, but where did you get the 0.025?
Okay, so if you take a look at my drawing, right?
Okay.
So it's 95% confidence level. So that means that the center part, this piece in here.
Oh, never mind. I get it.
You see it? Okay. Yeah. So that's 95%. And so what have I got left to put in the tails?
2.5%.
On each side, right?
Yeah.
I got 5% total, right?
Yeah.
And so
I got it.
Cool. No, that's good. It's good to make sure you ask questions like that. So. So back here, just to be complete, notice that if I did 97.5%, that would be up to here. You don't have to do this because it's by symmetry. We know what they both are now, but I just want to point out that if I had done Q norm of 97.5, okay, percent, I'm going to get the positive number.
Okay, I'm a little lost. Like, what is this just doing the same thing you just did?
Yep, I'm doing the same thing I just did, except for this time I'm getting you this guy.
Oh, you're just giving me the positive. Okay.
Yeah, here, think about it this way for a second, Damien. What if I said, what's the color? What's the color? The color is cyan. What is the area, that's cyan. If I keep coming down here, you with me? See, I got 95%.
Yeah, I'm following.
I got 95% here in the middle, and then down here in the red, I got 2.5%. So 95% plus 2.5% is 97.5%, right?
Oh, okay.
So if I put that into Q norm, then that gets me the other Z star, the upper one. But the reality is I don't need to do that because I just know, I know by symmetry that if I got the negative one, the other one is the positive one, right? They're plus or
Yeah,
minus.
it's gonna be, yeah.
Okay, so let's go write this thing up then. So a 95% confidence interval is going to be my point estimate, which is 98.2 plus or minus my Z star, which we just decided now we're going to round it off to 1.96, right?
Mm-hmm.
Times my standard error, which is 0.92 divided by the square root of 40.
All that lovely math.
Yes, it is. But it's all arithmetic, really, when it comes down to it.
Yeah, I know. I just some math things I kind of go, phew.
Yeah, exactly. So the thing to keep in mind, though, is that that's the point estimate,
Yeah.
right?
Yeah.
And in purple here, that's
Oh, purple.
the margin of error.
Oh, okay. That make because I was reading some people's posts and I'm like, where are they getting these things?
Yeah, that one's going to be the
Uh,
margin of error, okay? So if you did the
okay.
actual calculation now, we can go over into R and go let it do the calculating for us.
Yeah.
It's going to be let's call it SEM for standard error of the mean, okay?
Oh, okay.
It's going to be 1.9, I'm sorry, my bad. It's not SEM. It's going to be ME for margin of error. That's what we want it to be. So 1.96 and then times. R is not going to let you use setting things next to each other for multiplication. You got to actually tell it
Yeah.
you want to multiply.
When I've done the homework, it's done that to me. I'm like, it's the same operation.
No, this is no. You have to tell me. I will not just assume. Okay, so that's going to be the margin of error. The margin of error is the Z star, which is 1.96, times the sample standard deviation divided by the square root of 40, the right number in there, Mike. And then that's going to give us our margin of error. So if I take X bar plus that number and X bar minus that number, then I will get my confidence interval. So what we say is 98.2.
Yeah.
98.2 minus the margin of error. And
Oh,
then,
so you don't even have to type all that. You just type in ME. Oh, that's right, because you
because I just
assigned it.
did it. Yeah, exactly. I assigned it to that.
Okay.
And so there's your
Oh,
confidence interval.
that's cool. I didn't even, because what I've normally done is I've made a variable and I've assigned data to it, and I normally do one at a time. I didn't know you could do two at a time.
Oh yeah. And you see what I did is I just made a vector. I created a vector there, and that's why
Yeah.
it gave me both the numbers on the same line. It's kind of a cheater's way of getting it to make it look like a confidence interval. So
Yeah.
so it's saying that, with 95% confidence, the average body temperature is between 97.9 degrees Fahrenheit and 98.5 degrees Fahrenheit.
Wait, it wouldn't be. I guess no, never mind. I was overthinking something. I do that a lot.
So the thing is that when you get the interval, you got to realize that what you're saying is that 95% of the time, when I create one of these intervals, I'm going to trap the population mean. It doesn't say,
it's like catching fish, sort of.
uh, yeah, sort of. I mean, the analogy I kind of like is like, let's pretend you got a beautiful 1999 rust blue Corolla, okay?
Okay.
And you go out there, and 95% of the time, when you go put the key in, you turn the crank, it starts.
Yeah.
And 5% of the time, when you go put the key in there and you go to turn the crank, it doesn't start. So what that means, if you think about it, out of 100 times that you went out there to go start that thing, 95 of them it started, and 5 of them you had to go get a jumper cable or something. Okay.
Yeah.
So when I walk out and I go to put the key in it, what's the probability that it's going to start?
95%
Yeah,
of the time.
exactly. Yeah, it's 95. And I put the key in and I turn the crank and boom, it fires off. Now what's the probability that it's going to start?
Still 95?
Well,
Or no?
it actually doesn't really make sense anymore because it started, right?
Yeah.
Either it did or it didn't. And so,
Kind of like a Bernoulli variable?
well, yeah, sort of. But here's the deal.
Or
This this
trial,
this
I'm sorry.
this confidence interval, either it contains the true population mean or it doesn't.
Yeah.
Once the 95% was before you built the interval, you got a 95% chance of the process working, actually creating an interval that's going to capture the mean. You got a 95% chance it's going to start.
Okay.
Once you've turned the key, once you've created the interval, either it started or it didn't. Either it captured it or it didn't. Where my analogy fails is, you know, whether the car started or not. You're never going
Yeah.
to know whether or not your confidence interval actually captured the population parameter or not. That's kind of the bummer part of statistics, is that there's always a little bit of doubt. You can never get rid of that little bit of doubt.
Yeah. Wish I could do that. Sorry.
Okay, so that was a lot pretty fast, Damien. But hopefully, because it's recording this, if you need to, you can go back and take a look at it.
Yeah. Well, I always, any stats videos, I always save to my stats playlist. So
Cool.
make sure. But I think that does it for my questions. I'm pretty confident with what I have, and my reference